This is also a thick wire problem, but this time the current density is non-uniform. All right. So in all non-uniform problems, we have to somehow specify how the current is distributed over the cross-sectional area. And this is usually done by giving the current density as a function of position. So it's given in here. So it is this expression where capital A is some kind of a constant that we will also find. Right. Let's just remember that current density is really a vector, but I just describe its magnitude in here, not the direction, because there's actually one choice, one possibility for the direction of the current density. So it should always be parallel to the axis of the cylinder. So as a result, we don't have much choice in here. So as a result, that's the reason why we only specify its position dependence. So in that case, r is the distance, radial distance. So that means for any point inside the wire, r is the distance from the axis. So as a result, we give the magnitude of the current density at that distance. So here you can see that of course the current density is 0 at the axis, and it somehow increases linearly with the distance as you go away from the axis. So therefore there's higher current density at the edges, like that in here, lower in here, and much lower near the center, and 0 at right at the axis. So there's this kind of a current distribution somehow, and our job is to compute, of course, the magnetic field inside and outside the wire. But the first problem is, of course, to find a relationship between the constant that appears inside the current density expression and the total current. And when I'm solving that problem, I will essentially solve the whole problem, more or less. So as a result, let's just go over with this part. So as the first step, of course, I would like to show you how the current is kind of distributed. So this I don't know, this is a strange image. So the density of dots in here somehow indicates the current density. So you can see that there are more dots near the edge. So therefore, there's more current flowing towards us from this region. And there is less number, the density of the dots is smaller near the center, so therefore the current density is somehow smaller there, and somehow it should be exactly equal to 0 right at the axis. Okay, so how do we solve this problem? Well, first of all, let me just say this. When we would like to compute the current, like the total current that's passing over this whole wire, we essentially have to integrate the current density over the area. Right? There's this kind of an integral in here, j dot dA. Remember that the current is actually the flux of the current density. Some of the students actually make the mistake of writing this current as the product of the current density with the area. Well, in that case, of course, some of them would like that. Since the total area is pi r squared, they would write it down like that. But of course, this is wrong because the current density is not uniform, right? So as a result, if you would like to write down this kind of an expression, the current density at which location should be taken? Is it the edge or is it the center? Well, none of them actually gives you a correct expression in here. So to properly compute the current, you have to evaluate an integral. So that's the only difficult part of that question. And the whole purpose of actually solving this problem is to actually show you the method of integrating the current density. So what we would like to do is, basically we would like to divide this whole area into smaller areas, where on each smaller area, of course, on each smaller area, somehow the current density is constant. And in that case, I can multiply them And in that case, this formula would be correct. But in that case, of course, I have to evaluate some kind of an integral too. That's essentially what we do. But instead of choosing these infinitesimal areas as small pieces in here, we just choose them as well, circular in shape. So what we do is essentially we think of this whole cylinder as some kind of a leak. I made this analogy for the spherical, non-uniform spherical problems in the case of electric fields, if you remember. In that case, I made the analogy to an onion, but this time we have a cylinder, so therefore what we need to do is to consider this whole cylinder as some kind of a leak that is actually formed from these cylindrical shells. Right, so as a result, this is the cylinder, this is the three-dimensional picture. I'm just going to consider a small cylindrical shell in here. This is really a shell where the thickness is negligible, right? I know that the current density is constant over this cross-sectional area of that shell, so therefore at least on that part I can write down the total current as current density multiplied with the area. That's the whole method actually. So formally this is how we do, right? What I do is I consider a shell in here. Again, this is the front view, but what I'm doing is I'm actually drawing a cylindrical shell in here as a shell. So I'm going to use a different color to show the radius of the inner cylinder, that's R. I'm going to show the radius of the outer cylinder as R plus dr. Right? So I'm considering a cylindrical shell where inner radius is little r and outer radius is R plus dr, where this dr is an infinitesimal. Basically, this is going to be our, it's going to appear inside our integrals. And so as a result, at the end, I'm going to take the limit where this thing goes to 0. So when I'm writing down some formulas, I can assume that it is equal to 0. Again, remember that this is not a ring, this is a cylindrical shell. There's a long portion in here that we cannot see from this point of view. But we don't actually care because that's not what we are interested in. So let me use a different color like the red in here to show the area in here. So this is the cross-sectional area of that cylindrical shell. So that area in here, I'm going to show this with dA. That area is equal to the area of that ring. We have also discussed how to compute this. There's a very simple geometrical way of writing this thing down. This is essentially the circumference of that circle multiplied with its thickness. So that's 2 pi r dr. Right? I have discussed this at the limit where this dr goes to 0 in this limit. This is the correct expression. So as a result, I'm not going to discuss how this thing comes out at the second time. So as a result, let's just write this thing down. So as a result, let's say it like this: current on this shell. The current is flowing everywhere, but part of it is actually flowing on this shell. And let me show this current as di, because this is also would be an infinitesimal in the limit where dr goes to 0. That would also go to 0. So this d is just a reminder that this is infinitesimal. That's basically current density multiplied with the area. So that means current density is A times R. There's a collision of symbols in here, but just remember that this A in here has nothing to do with area. It's just a coefficient in the current density. In any case, area is 2 pi r dr. Right, that's the current. And to find the total current, I have to sum over all of this. So symbolically it is shown like that. But in any case, what I need to do is to integrate this expression. And then, of course, we have to decide on the integration limits. So let me do it in a new page. right? So let's say it like this. The current is basically, I have said that this is the current times dA, but in that case, we just choose these areas as areas of some rings. So therefore, these areas are in the form of 2 pi r dr. This is essentially the integral that we are going to evaluate. And in all cylindrically symmetric problems with the non-uniform current distributions, this integral expression is going to be the same. What are the integration limits? I would like to express the total current, and because I know the total current, so I would like to use this equation to find the coefficient A. So as a result, the integration limits are these. So let's just quickly do this. All right, so that's the integral, and that's equal to the current. So therefore, from here, we say that the coefficient A is equal to 3 over 2 pi the current divided by r cube. Okay, that's it. So then let's pass to part B. Right. Part B basically asks the magnetic field at a point inside the cylinder. So this is the central axis. So let's say that this is my point in here where the distance is r. Right? I would like to find the magnetic field in here. What is that magnetic field? For this purpose, I just choose an Amperian loop with radius r, which is basically identical with the magnetic field. So as a result, I just write down the Ampere's law. So that's B dot dl. That's equal to mu0 times the enclosed current. I know how to evaluate the left-hand side, but let me quickly go over this. So first, I convert the dot product into the product of the magnitudes. Then take the magnetic field out. Then see that this is basically the circumference of the Amperian loop. Right, that part is going to be the same for all cylindrically symmetric problems, obviously. So on the right-hand side, however, I have an enclosed current. That's basically the current that passes from inside this Amperian loop in here. So this is the current that passes over this region in here. I need to find this. It's not the total current, but what is it? I need to evaluate an integral. What integral? Well, we have formed the integral in any case. So that's basically the integral of, sorry about this, but I need to make a few changes in here. So that's 2 pi r dr. Let me first write it down like that. I have said that the integral is going to be the same, but the integration limits are different in that case. Let's write down what the integration limits. So I need to describe that surface basically. All right. So that surface basically has a radial range starting from 0, that's the axis, ending up at little r. All right. Let me erase this picture so that I can still use the same picture. But there's a problem in here. I have again a collision of symbols. I have used little r for this variable in here that expresses the distance of my point from the axis. Basically, this is a fixed quantity. It's not a variable actually when I'm solving this within this problem. So as a result, it's not something that changes. But there is another thing in here, another variable in here, but I have shown it with the same symbol. I need to introduce this thing to actually divide the cylinder into small cylindrical shells like a league. And then I need to use another variable to express the radii of these shells. So I need to use a different variable for that purpose. And so as a result, I cannot use the same symbol anymore. So as a result, I have to use a different symbol for the integration variable. All right, so for the current density too, I need to express it in terms of this variable. So, I mean, we don't have too many symbols, so as a result, I'm just going to use r prime in here. So as a result, r in here is, let me erase this picture again. R in here is the distance of my point from the central axis, which is fixed. And r prime in here is the radii of the cylindrical shells that I use in the integration when I'm computing this enclosed current. So as a result, these two are different. So r prime is a dummy variable. Once I evaluate this integral, I'm going to forget about this value, right? So it has only meaning within that integral. So let's just quickly go ahead and compute this. So this is mu zero. Integral is from 0 to r. Current density is a times r prime. This is 2 pi r prime dr prime. So this is mu 0, 2 pi a integral of r prime squared dr prime. I know that this is an integral r cubed divided by 3. Let's just formally write it as minus 0 as well. So as a result, on the right-hand side, I have mu 0 times 2 pi a r cubed divided by 3. And on the left-hand side, I have 2 pi r times b. So the 2 pi's cancel, and as a result, I can express the magnetic field as mu 0 times a divided by 3 times r squared. We have also computed the A coefficient in terms of the total current. So I would like to express the magnetic field in terms of the total current. So let's just go ahead and remember what A is. I think I can remember this expression. So I'm going to insert this value in here. So let me just do it in here. So the magnetic field is therefore mu 0 over 3 over 2 pi current divided by 1 over r squared and little r squared. So as a result, the 3's cancel, and what we get is, since I don't have space left, I'm going to erase this thing in here and write it in here. So the magnetic field is mu 0 I over 2 pi. I made a mistake in here. So this should be cube 2 pi r squared divided by r cube. All right, let me check this r cube thing. Yeah, it was r cube in here. All right. So that's the expression. So this time, of course, the magnetic field depends quadratically on the position. So what's the magnetic field outside? So again, this is the axis. I take a point in here, which is at a distance r from the axis. The magnetic field in here is little b. So for that purpose, I choose a Gaussian, Amperian loop. This is just a loop now. And write Ampere's law. All right, I don't want to spend too much time in here. So the left-hand side is, after so many steps, is B times 2 pi r. And the right-hand side is basically the total current in here. So all the current that's flowing on the cylinder is actually is enclosed. So therefore, the right-hand side is just does not depend on the position little r. Right? So as a result, we get the same expression. So you can see that we meet the same expression over and over again. So as a result, I mean, if you have a current carried by a cylindrical wire, and if that current has this cylindrical symmetry, the magnetic field produced at a point outside is the same as if this whole current is actually flowing through the axis by an extremely thin wire. So as a result, these two problems have the same solution. So it doesn't matter whether the wire is thin or thick, where the current density might be non-uniform as well. In all cases, the magnetic field outside has the same expression. Right, as a final point, let's just plot the strength of the magnetic field as a function of position. So inside it changes quadratically. There's a parabolic graph in here, and outside it just goes like 1 over r. So inside it is r squared, outside it is 1 over r. Let me also write down the expression in here. So the magnetic field strength is mu 0 I over 2 pi r squared divided by r cubed for points inside, and mu 0 I over 2 pi r and for points outside. Right. Please note that just note that note the dimensions, right? So this expression has the dimensions of 1 over length in here, multiplied with constant mu 0 I over 2 pi. And we have a similar thing in here. So we have an expression in here which has a dimension of 1 over length multiplied with mu 0 I over 2 pi. So as a result, the dimensions are the same. So it is important to notice these kind of things, because if there's a mistake that you have made, you can easily catch these by these kind of simple considerations. And also, r equals r, that special case right at the edge, I can use either of the two formulas and I'm going to get the same result. This tells you that the magnetic field is continuous at that point. So I can use either the formula inside or formula outside. I'll get the same thing.